Welcome to EPG Pathshala program in Linguistics. We are going to discuss a module from the course An Introduction to Computational Linguistics and Speech Processing. The coordinator of this course are Pramod Pandey from JNU and Professor Vidya-mitra Sharma from IIT Hyderabad. The module title is Concatenative Speech Synthesis. The author of this module is Professor Hemant Patil. I am Amardeep Kumar Singh, School of Computer and System Sciences, JNU, and I am going to present this module on behalf of Professor Patil. Let's get into the discussion. The outline of this module, which we are going to discuss on concatenative speech synthesis. In this module, we are going to discuss the festival speech synthesis system, domain-specific speech synthesis system, diphthong synthesis, and unit selection synthesis. We are going to discuss the unit selection synthesis, shortly named as USS, in detail rather than just briefing about it, as we will be doing for the first three synthesis system. For USS, we will be going to discuss the cluster unit selection method, synthesis stage, prosody modification, and the straight portion. Let's get into the introduction and the whole discussion. So, we are going to discuss the module Concatenative Speech Synthesis. So, first of all, it is a method of speech generation out of the three methods that we have described already, which are parametric speech synthesis method, concatenative speech synthesis method, and a statistical parametric synthesis system. So, in this module, we are going to discuss the concatenative speech synthesis system. The concatenative speech synthesis is also known as the natural sounding speech, primarily due to concatenation of natural speech sound units. It is a TTS technique where speech is synthesized by joining speech sound units together. The basic speech sound units can be a phoneme, diphthong, syllable, or even a word. The duration of the units is not strictly defined and may vary according to the implementation, roughly in the range of 10 milliseconds up to 1 second. Now, the synthesized speech by concatenating the waveforms of units require a large selected corpus from a single speaker in a uniform recording environment. The basic requirement behind using a large database is that with a large number of speech sound units available, it will be possible to capture large prosodic variations and spectral characteristics that will lead to synthesizing more natural sounding speech. This most important issue to be solved to make this concatenative synthesis approach effective is the selection of appropriate units from the database. Concatenative synthesizers, however, have a fixed inventory and cannot reasonably be made to produce anything outside their predefined vocabulary. In the next section, we discuss the concatenative speech synthesis system developed under the commonly used festival framework. The festival speech synthesis system. It is an open source framework developed by the Center for Speech Technology Research, University of Edinburgh, UK. The festival is a language-independent speech synthesis engine that can be used for developing text-to-speech synthesis systems. It is highly flexible with a modular architecture and includes examples of various modules. Festival is most advanced for English, that is both USA and UK. However, it also can be used for other languages. It is easy to configure and allows the addition of external modules to build voices for new languages. So there are studies across languages to determine the best possible unit in a language. Depending on the type of a unit, the type of concatenative speech synthesis can be divided into three variants of concatenative synthesis, namely domain-specific synthesis, diphthong synthesis, and unit synthesis. Now we will be describing briefly the domain-specific speech synthesis. This is a type of concatenative speech synthesis method where only limited corpus is required for a small specific purpose rather than using it for a general speech synthesis application. An example of domain-specific speech synthesis can be thought of the announcements made at the railway stations for arrival, departure of a train, talking clocks, etc. The database can be built in this case with few numbers, station names, etc. The naturalness of these domain-specific systems is high because the variability of sentence type required is limited and they closely match the prosody and tone of the original recordings. In addition, it is likely to ensure that all the units needed for good quality synthetic speech is present in the database. The domain-specific synthesizers cannot be used for general-purpose synthesis because of the limited words and phrases with limited variation in the databases and can synthesize only the combination of words and phrases for which it was targeted. Now we'll describe the diphone synthesis. So a diphone is a pair of phonetic sounds that are adjacent to each other in a vocal sequence. Using a diphone synthesis uses a least required speech database containing all the diphones, sound-to-sound transitions occurring in a language. For example, the number of diphones depends on the language. The diphone synthesis speech databases consist of only one unit of each diphone occurring in the language. For example, with a 44 inventory, one could collect a 44 into 44, that is 1936 diphone inventory, and create a synthesizer that could speak anything. That is, all the phone transitions are covered such that any possible sequence of speech sounds in the target language could be produced. As diphones capture the transitions from one sound to another, it captures the acoustic quality of an individual to a good extent. The motivation for using diphone, which is two adjacent half phones, is that the center of a phonetic realization is the most stable region, whereas the transition from one segment to another contains the most interesting phenomena, and thus the hardest to model. The diphone then slices the units at the center region of relativity stability rather than at the unstable phone-phone transition, where the co-articulatory effects appear. This model is advantageous with respect to the database size, use of small speech units to be able to synthesize all possible phonetic and prosodic variation in the language with a limited database size and prosodic flexibility. However, diphone synthesis undergoes glitches due to the concatenative synthesis, degraded naturalness, and the machine learning nature. During synthesis, pitch and duration modification can be used to obtain a desired prosody. This can be achieved by means of digital signal processing techniques such as linear predictive analysis, pitch synchronous overlap, and ADD, which is PSOLA or MBROLA. There have been other approaches also that use recent techniques such as pitch modification in the source domain using discrete cosine transformation or the use of harmonic noise model. Now we'll describe briefly the unit selection synthesis. In contrast to diphone-based synthesis, in unit selection, there are several instances of the same speech sound unit and some mechanism is used to select between the several examples to produce superior quality synthesis system. The USS will be described under the following subheadings. The history, we'll first describe the history, then the cluster unit selection, the synthesis stage, and the prosody modification. So let's start, or rather give a glimpse of the history of USS. The advanced telecommunication research that played an important role in development of the unit selection approach, the initiative in this direction was led by the work reported in a research paper which provides optimal choice of a unit sequence for an input phoneme string using appropriateness measures and followed by use of dynamic programming in unit selection. Later in 1994, the researchers developed a general purpose synthesis system and development platform known as CHATR system, which uses one particular method for selecting between multiple examples of a phone within a database. In 1996, The research work directed towards incorporating the unit selection framework into the CHATR system in English and Japanese. In fact, this is known to be the first complete unit selection system in English. The units in a synthesis database are considered as a state transition network in which the state occupancy cost is distance between a database unit and a target, and the transition cost is an estimate of the quality of concatenation of two consecutive units. This was the first pure unit selection system from linguistic perspectives, as it did not use any signal processing for procedure modification. Then the synthesis system started establishing elsewhere, starting from the festival framework at Edinburgh, AT&T, NextGen system, etc. And since then, study has progressed significantly towards using and improving the unit selection speech synthesis systems. Now, let me show you the block diagram of unit selection based TTS system in festival synthesis framework. As you can see, this block diagram shows firstly the input text, which goes into the processing, the text processing module, which includes processing the input text collected from various online sources, various non-standard words, punctuation, abbreviation, tags, smileys, etc. needs to be normalized. The phonetic analysis refers to generation of sequence of speech sound units from the text. This can make use of a dictionary, as in case of English, where the mapping from orthography to pronunciation is not always straightforward. For language rules, that is letter to sound rules, can be used as done in Indian languages. Prosodic analysis includes using intonation and duration modeling for the given text. Finally, the speech generation section can be rule-based, concatenative or statistical approach to synthesize the speech waveform. Now, in the following section, we will discuss the speech generation by concatenative in the unit selection speech synthesis system. So, now we will describe the cluster unit selection. In cluster unit selection, the speech sound units can be clustered based on the acoustic distance between the speech sound units. Here, a model is built that predicts which acoustic waveform units are needed or rather relevant to synthesize a given context. The idea is to take a recorded speech database and try to cluster each phone type into groups of acoustically similar units based on the non-acoustic information available at synthesis time, such as phonetic context, prosodic features, and higher level features such as stressing, accent, and the position of a word. This is a re-implantation of the techniques as described in the research paper. The actual features used may be changed and experimented with the definition of acoustic distance between the units in a cluster. A weighted Mahalanobis distance metric is used to define the distance metric to define the acoustic distance between the two units of the same class. Now, you can see that the cluster unit selection is done using this A distance vector, or rather a distance measure. So, considering U and the norm of V as two units of the same class, and if the number of frames in V, that is the mod of B, is more than the number of frames in U, that is the mod of U, then the acoustic distance is given by the following formula, as you can see on the screen. Here, the WD is the duration penalty weighting the difference between the length of two units. Fxy of U, or of frame X of unit U, Stj, is the standard deviation of parameter J, Wj is the weight of the parameter J. This measure gives the mean weighted distance between units, with the shorter unit interpolated to the longer unit. Now, in this context, classification and regression trees are used to represent the clusters in festival framework. The cart method is used to build a decision tree for each type of speech sound unit present in the speech corpus whose question minimizes the distance of the subclusters at that point in a tree. The leaves of this decision tree, let me show you the decision tree first. Now you can see the tree. So the leaves of the decision tree are the list of candidate units which may be picked during concatenation in order to generate synthetic speech. The card trees can be built based on different features of speech unit, such as the position of a speech unit in word, phrase, sentence, context of a speech unit, type of a speech unit, etc. Now we have come to the synthesis stage. So in general, there is a large database of speech with variable number of units from a particular class. This approach selects the best sequence of units from all the possibilities in the database and concatenates them to produce the synthetic speech. This selection algorithm has two parts, namely to find units in the database which best match this target unit, to find units which join together smoothly. In the unit selection framework suggested by Hunt and Black, the entire database of units is searched to find the best possible sequence of units. They suggest a concept of a target cost given by T, that is how close a database unit, which is UI, is to desired unit target, which is ST, and a join cost represented by J, that is how well two adjacently selected units join together. Now there is this figure which shows a brief idea of the target and join cost. You can see the diagram on the screen. It is the representation of the target cost and the join cost. Okay, so in this, the unit selection process is designed to optimally minimize both target and join costs. For the given sequence of target units, the unit selection algorithms selects an optimal set of speech units that best matches the target speech unit specification and with the other speech units in sequence without any perceptual distortion. For every target unit, the unit selection algorithm first considers a list of candidate units, one from the speech corpus. The candidate unit which minimizes the sum of two costs, which are target cost and join cost, is then selected as the final choice. Now, there are some fallback of speech sound units. We'll describe them here. Even if a large database is collected for the USS system building, it is not possible to cover all the possible sound units in a language. In the unit selection based synthesis approach, only the sound units that are present in the speech corpus are available for synthesis. In order to synthesize everything that is all possible text, at least one instance of each sound unit must be present in the speech corpus. However, unlike number of phones, number of larger units are not fixed. Therefore, to compensate for the missing sound unit, one possible solution to this could be substituting a missing unit with that of a similar unit. For example, if the diphone, which is DIH, were missing, it could be replaced by a similar diphone of DIY. However, such a substitution may be perceived by the listener or may even result in recognizing wrong word. An alternative to this is also known as unit backoff, where new units are made from the existing units. Instead of unit substitution, the second half part of DIH could be used with first part of DIY to create DIH, that is, using the half phone case. Now we'll describe the prosody modification. So prosody is the study of rhythm, intonation, stress, and related attributes in a speech signal. However, it should be noted that the definition of prosody in speech is evolving almost every day, which explains the challenge associated with exploiting speech prosody to improve quality of TTS voice. The TTS systems have only text as input, the various reasons that may contribute to human accenting decisions, and these are not well understood. Most TTS systems change the pitch counter of a sentence only by reference to its final punctuation. For example, sentences ending with dot, that is a full stop, may generally end with a flat pitch, while sentences with a question mark may end with a rising pitch. Beyond these sentence-level prosodic decisions, the TTS systems should attempt to vary such other features as pitch range, speaking rate, amplitude, and voice quality in order to convey the variation in intonation that humans are capable of producing and understanding. Many TTS synthesis systems use algorithms to vary prominence based on the information in the word, sentence, or introduce additional phrase boundaries based on simple position or syntactic information. In case the prosodic breaks are automated, then the problem is handled. However, manual prosodic labeling is very labor-intensive, and variety of prosodic behavior that humans vary in normal communication is very large. The relationship between such behaviors and automatically detectable features of a text is not well understood. Failures of prosodic assignment accurately in the text may represent the largest source of lack of naturalness in TTS systems today. The current section concatenates concentrates on the signal processing techniques used to change the pitch and timing information of the waveforms. Now we'll move on to describing pitch synchronous overlap and add method, which is the PSOLA method. So this PSOLA has two variants. That is time domain PSOLA, which is TD-PSOLA, and frequency domain PSOLA. So time scale modification, the length of the speech signal can be increased by duplicating frames and then add the frames to get an increased duration of the speech signal. Similarly, the duration of the speech signal can be decreased by removing alternate frames and then add remaining frames. The result is a speech with shorter duration. However, by this factor, scaling by up to a factor of 2, twice longer or shorter, can be performed without much noticeable degradation. Odd factors of scaling will be difficult to implement. Now, let's talk about pitch scale modification. The pitch of the speech signal can be changed by recombining frames on epochs which are set at different distances apart from the original ones. For example, a research paper assume a speech segment with a pitch of 100 Hz, which is 10 microseconds between epochs. As before, we perform pitch synchronous analysis with a Hanning window. If we place the window frames 9 milliseconds apart and overlap add, we will obtain a signal with a pitch of 1/0.009, which is approximately equal to 111 Hz. Conversely, if we place the frames 11 milliseconds apart, we will obtain a signal with a pitch of 91 Hz. Now let me show you this picture, which shows the simultaneous pitch and timing modification. The time and pitch modification technology can be shown in this picture. As with the time scaling, the pitch scaling by up to a factor of 2 can be performed without much noticeable degradation. Now we will describe another model, which is sinusoidal model. So it considers the summation of the cosine curves, and you can see the formula for the summation, which is represented by S of n and with a cap, which is equals to summation over L equals to 1 to capital L of AL cosine of omega 0 L plus phi L. It is clear that AL represent the amplitude, W0 represent the frequency, and the phi represents the phase. So the pure sinusoidal models used to create an artificial signal is this one, which is represented by E. The window function Wn is the center and this analysis can be performed on comparative short frames. Then the harmonic plus noise model, which is also known as in short HNM. This method was specifically developed for TTS. In addition to the harmonic part discussed above, the noise part models the fact the real speech can have specific temporal patterns. Thus, addition to the harmonic component, a stochastic component is added to give where the noise component is assumed to be Gaussian. Now, in this model, there are a few steps in the analysis part, which includes the determination of voiced or unvoiced frames as U, V or V, then the determining the highest harmonic frequency in the voiced frames, and estimating the model parameters. Now let's talk about this straight. So this straight is a high quality vocoder that decomposes the speech signal into three terms: a voice a smooth spectrogram free from periodicities in time and frequency, an F0 contour and time frequency periodicity that captures spectral shape and temporal envelope of noise. This straight does not extract phase information, instead uses a minimum phase assumption for the spectral envelope and applies all pass filters in order to reduce buzz timbre. So in this module, we have briefly described the concatenative speech synthesis system, which is the main time consuming part in the building of the TTS voice system. So in this synthesis system, we have described how the main stages of this TTS voice building system requires firstly selecting the speech sound units, then making a text corpus, then finding a voice talent or a speaker, a suitable speaker to record the sound for synthesis, and then the last part, which is the most tiring part that comes up, is the labeling of these sound units. Now, after the labeling, we have also shown the process of clustering the sound units in order to make meaningful speech signals. However, this concatenative speech synthesis is one of the method, and currently another parametric approach, statistical parametric approach, which is HMM based speech synthesis system, is also being used. We will be describing the HMM based method in the next module. Thank you.